Here's the next video in the EM algorithm, the examples part. We're going to look at the bivariate normal distribution, and we're going to try to use matrix notation to help solve this, simplify some of the notational issues. Otherwise it gets a little cumbersome. And here's our data. So we have each observation kind of goes across this way, and they have an x1 and an x2. And so as we go down, there's there's n total observations, and here there's a section where x1 is missing for some patients or observations, but they have the x2, and here this group, they have x1 but not x2, and there's s of these, r of these, and u of these, and u plus r plus s equals n. And what we're going to try to do is use the EM algorithm to estimate the parameters of a bivariate normal. So here's the mean vector, has two components, mu1, mu2. Here's the covariance matrix, has four components. This is sigma 1 squared, which is the variance of the first component, sigma 2 squared, which is the variance of the second component, and sigma 1, 2 is the covariance between the two. And this is a symmetric matrix, so these two covariances are equal. And we do need to make this a positive definite matrix, and so the relationship that the correlation is equal to the covariance divided by the standard deviations is this. And yeah, and then so here x is a random variable that has two components, and x is bivariate normal, and this is an observation. So the ith person, the ith observation, has two components, two numbers that we're collecting, and there'll be n of these vectors, 2 by 1 vectors. Okay, so in matrix form, your matrix notation, f of x, which is this vector here, is bivariate normal, and that's set up like this: 1 over the 2 pi. Now this is the determinant of the covariance matrix raised to the 1/2. So it could be 1 over this, or the the square root of that, e to the, and then these are all matrices. So this is a a transpose of this observation minus the mean vector. This is the inverse of the covariance matrix. Notation, we'll just call it multivariate normal with mean vector mu and covariance matrix that. So, but when we're looking at n of these, and they're all independent, so it's n of these multiplied together. So the 2 pi, and then there's n of these determinants, and then it's the sum of these vectors. So because it's e to the power and there's n of them, then you combine the powers by adding, and that's what we get here. Now the log likelihood is the log of this, and whenever you take the log of a product, it's the sum of the logs, and the exponents come out front. Now here, for this, I don't think we need to do this, but I want to emphasize this, that negative I put in the determinant. The determinant of sigma is the same as the determinant of the inverse of sigma. And I do that because technically when we maximize this, it's easier to take the derivative with respect to sigma inverse, and then that helps us find sigma. So that's just a little subtlety there. And then the log of e, it goes away, and we just get this. And because the video is going to run kind of long, I'm not going to actually drive the maximum likelihood estimates, but it is pretty cool to do that. And what's interesting is that it can be tricky is the derivative with respect to sigma inverse. So this piece here you end up having to use what's called a trace function to help rearrange this, take the derivative, and then the derivative of a determinant is also a pretty interesting derivation. And maybe I'll put that in another video, but not for this time. You know, this involves the adjoint matrix, which is, it's like the transpose of the cofactors, and the cofactors deal with, you know, the minors of the matrix. Pretty interesting. So here, whenever you're doing the EM algorithm, you know, we have this joint likelihood right here, but we want to rewrite it in terms of what we can observe and what we can't observe. So if we have our x1 through xn, and then that, you know, it's the rows here, but if we think about this as component one or section one for component one, section two, component one, this would be section three for component two. We can kind of rewrite these as y11, z21, and y means we observe it. So it's the first section, first component. Z is missing, so it's z21, it's the second section, first component. And here you get y12, y22, and z32, the third section, second component, is missing. So we can write it in terms of this. So the y's are observed and the z is missing. And this is pretty important to be able to do that. In deriving the bivariate Poisson, or using the EM algorithm, the bivariate Poisson, we have to make a little transformation to write it in this fashion. The E step is the expected value of the log likelihood, and then it's in with respect to this function here, where it's the missing given the observed and actually the parameters, or an estimate of the parameters. So I don't have that there. These are independent, so they can be broken apart, the product, and then, you know, these two are independent of that, and you know, and 3,1 is independent of 2,1, and so anyway, it can be rewritten like this, and then these end up being, you know, if we observe them, would be normal distribution. So this first one is normal with this mean and this variance, and this one is normal with this mean and this variance. And in another video, which I'll link into the description, I derived that these are normally distributed with these mean and variances. So now we want to take the expected value of these, and so here's the first one. And the expected value of a mean, of a normal, is just the mean. And then the expected value of 2,1 squared is the variance plus the mean squared. And then we can do this for this this equation here. The mean, expected value is just the mean. Expected value of z32 squared is the variance plus the mean squared. Okay, so these will be, we will need to substitute these values into the log likelihood for the missing observations. Okay, so let's look at that. So the standard notation is this, where we find a Q of theta given our initial estimate of theta, and it's the expected value of the log likelihood function, and it's with respect to missing given our observed, you know, with our parameter, initial estimate of our parameter. So the expected value of the log likelihood is the expected value, and this is it. Now, before it was just written as one sum, so sum from 1 to n of all these quadratic forms. But I broke them up into the 3 sections. So this is section 1, where these are actually all observed, and then this is section 2, where the first component is missing, the second one is observed, and this section is the third section where x1 is observed and x2 is missing. Okay, so now I do a little step to show you. Anyway, you use, I think it's easier to use this when you're taking the maximum likelihood estimates, but I do it here sort of for illustrative purposes. The trace is that you add the diagonals of your matrix, but these are scalars, so it's just one number. So the trace is actually the number of just the number. But when you take the trace of, say, these, the interesting property of the trace is you can change around these vectors and matrices. And then it ends up, to me, just being a little more intuitive when you take the maximum likelihood estimate. So here, so this first one here, when you take the trace of this, then I like to bring this, the sigma inverse to the front. Then you actually have to switch these two vectors to make the multiplication work, and that's what you get here. And then it's this product, you know, summed over the observations 1 to u, ends up being a covariance matrix, not divided by n yet, or u in this case. And then you take the trace of each of those. Now, this is the first section where everything is observed. This is the second, this is the third. So we're going to rewrite this matrix here to highlight the fact that we don't know the first observation. Okay, so this star is actually going to be this section, and the double star is this section. It's a matrix. So star 1 is if you were to multiply this out, which is this, you can show that it's this. And usually you write it like this in terms of the squared, and then this is the cross product or whatever. But we don't know the x1 component, so we multiply out the squared. And this piece here, the x1i, is unknown, that's unknown, that's unknown, that's unknown. The x2s are known in section 2. So we're going to replace this x1i squared with the expected value of that we just calculated before, and we're going to replace this with the expected value. And so for the third section, the second component is unknown. So this matrix can be rewritten like this, and I expand the second part to illustrate that the x2 component is unknown in the third section. So we're going to have to replace that with the expected value of x squared. This is the expected value of x. Okay, so to find the expected value, and also note that since there's no, you know, this is constant, this is constant, this is a constant because these are known, and then you just, when we take the expected value of this, it's simply replacing these unknowns with the expected value. In the same way for this, you expected just that second component. So we're going to replace, in star, we're going to replace the x1i squared with its expected value, the xi with its expected value, and then in the second asterisk, we're going to replace it with its expected value, and then that's it. And then we maximize it. So to maximize it, first of all, we calculate the mean vector, which is you add up all the vectors and divide by n. That's an estimate of your mean. But remember, this is the first section, we know both of those. In the second section, we don't know the first component, so it's replaced with its expected value, and we know this. And the third component, we know the third section, we know the first component, not the second component, so we have to replace with its expected value. And zoop, and then there's an estimate of the mean. So for the maximum likelihood estimate of sigma squared, it's actually, if we knew everything, we'd just sum from 1 to n of these observations, but we don't. So we have to sum the matrices over section 1, section 2, and section 3. But in section 2 and 3, we have to replace the missing with the expected value. So now these are updated estimates for our parameters. So you take these updated estimates and you go through the E step again and make an update, and then you come to the maximize step, and then you come up and then you estimate these again for the next time, and then you just repeat and repeat until these parameter estimates converge. And now let me illustrate this in a short little R program that I did. Hello, we're in R on a Linux-based machine, Ubuntu specifically, and we're going to look at the EM algorithm for the bivariate normal case. I want to load this library extra distributions because it has a bivariate normal distribution in there that makes it convenient for generating bivariate normals. And it's why reinvent the wheel. Here we're going to look at 500 observations, and then next we need to consider how we're going to make some of these observations missing. And so what we're going to do, remember, U is the first section, R is the second section, S is the third section. U, they're all observed. R, let's just make it roughly 10%. I call it temp R because that's the number that we'll make missing. And then for R, we create a sequence so I can quickly extract those specific observations from the matrix, data matrix. And S is going to be the number missing in that third section. And again, I'll just make it 10%. So let's look at that, and then the number U would be n minus these numbers we just calculated, so that's temp U. And then this creates a sequence from 1 to 400 and puts it in U, and then we create sequences for R and S. And that just makes extracting the variables much easier. So now we need to create our data, and I'm going to create it with a correlation of 0.4, and here -5 for the mean 1, 14 for mean 2. The variances, this is S1 1, so that's sigma squared. For the first component is 3, sigma squared for the second component is 4, and then I back calculate to find the covariance. And I do that because you want to keep your matrix positive definite, otherwise things don't work right. So here is here's how you generate the bivariate normal, different means. Here they want standard deviations as opposed to variances, so we just take the square root. And they want the correlation. So we generate n observations, which are 500. Boom, store them in R. And I'm going to store what we just created into, I'm going to call it original X, so we can get maximum likelihood estimates of our original data and see how close they are when we're just randomly putting missing observations in there. Now, this is how we put the missing observations in X. R is the second section, first component, put all missing. S is the third section, second component, put all missing. So done. So now in the EM algorithm, we need initial guesses for our parameters, and our parameters are the mean first component, and this is T is like our temporary first guess. Mean for the second component, the variance for component 1, the variance for component 2, and the covariance for just covariance. And I put them all at 1, and I have experimented with different values and it all converges to the same, so it's pretty stable. And so I'll just keep them all one here. Now here's the section for non-missing, and it's not going to change because we observe the data. And so we want the mean of the first component, or the first mean of the first section, component 1, mean of the first section, component 2. So let's put those in. And here, XU is the data for our section 1, which is this. Now I want to subtract the mean from the first component and the mean from the second component, and the way I had to do it is I had to create two columns, with the first column mean 1 and second column mean 2. And so this is like x minus the mean. That's what this, and then just the covariance of that data we just created, and I'm taking it times n minus 1, or basically u minus 1, because the covariance divides, but we don't want that in our initial guess. So there's sigma. Now we're going to EM algorithm, we're going to rep it 300 times, and then we're going to first work on the mean vectors here. And so this is section 2 where x1 is missing. So we know the mean for the second component in section 2, so let's put it there. And then this is the z, the expected value and the expected value squared. That's what this is equal to, and we're going to replace the unknowns with these components. And then the third section where x2 is missing, that we know the mean of the first component, or we can calculate it, and then here we have to take the expected values. So this is the unknown, or the unobserved, second section, or not section, but second variable that's unobserved, and this is z squared. And now we need to update our mean parameter. So the mean of the first component is, here's our data for the first section, variable 1. This is missing, so we substitute it with our expected value of each of those. And then the third, we know it, so we just use that data. And then this is an update for component 1. And then for component 2, these are observed, and this is missing, so we substitute the expected value of that for our data. And that's this creates an update to our original guess of 1, 1 that we used before. Now we need to update the covariance matrix. Now remember, there were 3 little pieces towards the covariance, and this is the second one where x1 is missing. And so we create a matrix. So this is the top left, and then this is the off diagonals, and we rep it twice because that's the upper right and the lower left, and then this ends up being the lower right, where we just take these are observed, and we just take the sum of the squares. So we run that, and now we estimate the third section, the covariance of the third section. And so again, this is the upper left, which is observed. These are the off diagonals, and now notice that we don't know the z, the second component, so we have to estimate it. Here we know the first component. Anyway, so we run that, and now to update why am I running it? Oh well. So then we take what we just updated, and so this here is our estimate for the sigma covariance matrix. But then I take the top first component, so this is the variance of the first component. This is the covariance, so it's the off diagonal, and this is the variance of the second component. And then we're going to run this 500 times, then we're going to print it out. And let me show you what we get. So it runs and boom. So remember we were it was negative 515. So this is our EM algorithm estimates here. So negative 4.8, which is close to negative 5. This is close to 15. And we had a 3 and a 4 as our variance estimates. And it's pretty close. And it's what's pretty amazing, that's pretty darn close to our original data. So this is maximum likelihood of our original data. And 414, 423, 2.73, 2.78. The mean vectors are very close. To me, it's just amazing how that works. And let's run that again. We're going to do it a few times here. So the second time we ran it, negative 5 and is it 14 or 15? Oh, it's 14. Okay, so I'm even closer than I thought. And then 3 and 4, this is the original, this is our EM algorithm, and to me, that's so amazing. Now there's one other piece, so we don't get the going too long. What is done in practice is, I'm going to call it a simple substitution. So the missing data for, say, the component 1, what they do is they put just the mean of component 1 for all the missing, and then for component 2 that's missing, they just put the mean of the other observed values in for the missing. See, they don't factor into that squared component. And if you think about it, if you're going to put the same value over and over and over and over, that's going to reduce your variance. So this next section is putting the mean in place of the missing values, and this is what we get. And notice that the covariance, the variance of 1 is 2.6, this is 2.9. This is variance of component 2 is 3.9, and this is 3.6. So it's smaller. And matter of fact, every time we run it, the estimates are always smaller because it has to be. So let's run the whole thing again. And these are the variance components, the EM algorithm, so 2.9, 3.6. This is the original data, 2.9 and 3.65. So it's really close. And this is if we use a simple substitution, we get 2.6 and 3.2. Now, why is that relevant? So let's say we use our data now and do hypothesis testing. Well, because the variance is smaller here in the sort of the silly substitution, it's going to make the test more powerful, falsely more powerful. And so it's not the appropriate approach. Anyway, I'm running long. I will talk with you later. I hope you enjoyed it. Like the video. Please subscribe. And I think I have 1, maybe 2 more examples on the EM algorithm. All right.